Hi there, during this session I'm going to be talking about magnetic and electromagnetic fields. To start with, I'm going to talk about magnetic fields generally as a whole, and then more specifically I'll be talking about certain fields, electromagnetic fields, as pertained and required by the IB Physics syllabus. So let's think about what a magnetic field is first. By definition, much like gravitational fields and electric fields, the region around a magnet is where a magnetic effect takes place, and this is known as a magnetic field. Now, a magnetic effect only interacts when there's magnetic material involved. Okay, so a magnetic material will experience a force when in a magnetic field. The picture we see here is a good example. Iron filings, iron can feel a magnetic field, so what happens is that iron filings naturally respond, if they're small enough, to the magnetic field around the magnet, which is shown here, and we can start to get some idea of the magnetic field lines. We'll go into this in a little bit more detail in a moment. So, continuing with the idea first of all of a bar magnet, just to get some ideas across. A bar magnet will have some magnetic field lines stretching out from it. Now, the direction of the field lines is really important when we're talking about magnetic field, because what happens is a magnet must have a north and a south pole. It can't have one pole, it must have two poles, and so the magnetic field lines will always travel from the north pole to the south pole. So those lines indicate going away from north and to south. There's unfortunately quite a lot of north-south confusion, which I should clarify at this point here. When I talk about the north and the south pole, we often think about a compass. And a compass responds to a magnetic field really effectively. It responds to the Earth's magnetic field. However, if we put a compass around a magnet, which has a distinct north pole and south pole, we'll notice that the arrow pointing towards north will point away from the north pole, and the arrow pointing towards north on the compass will point to the south pole. And those compasses each kind of indicate the direction of the field lines in that location. Now, that might be a little bit confusing to some people. You're going to be going, why is the north arrow not pointing towards the north pole? Well, that's what we've got to remember, that our magnetic north pole is technically a south pole. So what happens are compasses which will search for a south pole of the north pole of a magnet is actually a south searching pole. A little bit confusing. Hopefully you'll get your head around it. It's one of those little traits that you have to be aware of, that our magnetic north pole and the direction which our compasses point north is the north direction, but it's actually pointing towards a south magnetic pole. So a little bit of confusion there, but just to clarify that point. So we're going to be talking about electromagnetic fields in detail. Now, an electromagnetic field occurs because a moving charge gives rise to a magnetic field. Whenever we have a moving charge, so that's an electron moving or current flowing of any sort, then it produces a magnetic field as well as the electric field caused by the charge itself. So these are the things we're going to be thinking about. The field lines created by electric charge moving. Start off with, let's think about a typical wire. Now what happens if there's current flowing through the wire? That means a magnetic field will form around that wire. Now, because, and the trick here is that the magnetic field does form loops around the wire. There's no north or south pole in this situation, it creates a loop, but the important thing is the direction of those arrows. And the way to remember it is by using your right hand. If you have your right hand coming up, okay, what happens is that the thumb will point in the direction of the current and your fingers will point round in the direction of the magnetic field. So that's how you can remember how to map out a magnetic field around a wire. Now, if we get things more complicated now, we go from a wire to a single loop conductor. Now here, there's two sets of thinking, but basically you're going to use the same kind of idea. If we use our right hand and consider the direction of the current flowing around, what we'll see is we can see that the magnetic field lines will flow through the coil of wire depending on which direction the current is flowing, which you can again use by just thinking about your right hand and pointing your thumb in the direction and curling around your fingers to follow the path of the magnetic field lines. We're going to go another step forward. So if we have a solenoid, which is a many-looped conductor, what happens here is, again, if you consider the direction of the loop, what you'll have is the direction of the loop allows you to think about the direction of the field lines which are taking place. So as you can see with a solenoid, what we have here is quite clearly the field lines flowing away from one side and back towards the other side, flowing around and through the solenoid. In the center of the solenoid, we have, actually, we just have straight lines. So we have a consistent magnetic field there, but all around the outside, we have what looks a lot like the magnetic field you'll find around a typical magnet with a north and south side. Now there's a few tricks to try and remember this. One is just thinking about the first coil and then working out which direction that is using your right hand. Another method would be to think about, again, your right hand, but this time I think about the loop of the current flowing through, and then the field direction becomes the finger which you point. So imagine that right hand grip again, and that right hand grip allows you to think about the current direction, and the field direction will go with the arrows. So that's again another helpful little tool. Some people think about, and I find this one tricky, is to consider yourself looking at the either end of the solenoid and recognizing that the direction of which the current is flowing around shows either a north side or a south side, depending if it's going anti-clockwise or clockwise. I find that the most difficult to spot. But those are the ways for you to bring together the idea of the shape of a magnetic, and in particular an electromagnetic force.